This talk is in, let's see, there it is right there. This talk is a combination of two survey teams, the Dream 2 team at NASA Goddard and the Vortice team at APL. Dana Hurley kind of straddles both of them here, both teams, she's on both. Really this is an offshoot of our last year's forum talk where we actually talked about the Orion ion cloud interacting with a near-Earth object. And there's so much interested in the water ions that come from Orion that we decided to address the neutral water interactions. So really, this is a prequel to last year's talk. Let's see. There we go. Now, Michelle Gates did a great job describing the asteroid redirect mission, so I'm just going to show you the bat diagram here. Just real quick, there's a capture craft that's going to go off and capture an object of a few meters in size, either pick up a whole object by intercepting it directly or picking up a rock from a larger asteroid to then drop it off in a distant lunar retrograde orbit, maybe around 2020, in the mid-2020s or so. Like the moon, though, you have to remember that this asteroid, this body, actually has a fragile environment. You know, the surface could be a rubble pile, loose regolith, particularly if it comes back in that bag. But the thing that we also are concerned about is how the spacecraft outgassing could affect the NEA in terms of surface contamination, particularly putting water and water dumps directly onto the surface material. And our reason for concern actually goes back, believe it or not, to the mid-'80s when a number of us on the Dream team worked on, back then, the Space Lab 2 mission. And we, back then, they deployed the plasma diagnostics package, and we recognized that the shuttle, with its outgassing, was a huge, really, an artificial comet. That's the way Lou Frank described it back in '89, with nominal water densities in the vicinity of the shuttle of on the order of 10 to the 9th particles per cc, and even out at a kilometer, maybe about 10 to the 6th particles per cc. Just for context here, LADEE, when you talk about the atmosphere of the moon near the surface, you're looking around 10 to the 4 particles per cc. So you're talking about an exosphere that's maybe a factor of 100,000 times higher carried out by the human system. And then when you have large water dumps, like STS-128, the Discovery, dumped about 70 kilograms, you're talking about all this curve maybe going up by another factor of 10 to the 5. So Orion, if it's anything like if you use the shuttle as an analog, will most likely be the dominant atmosphere, dominant exosphere that is interacting with the asteroid surface. Just to show you this, there on the web, there are all kinds of images of this water dump from Discovery. Here's the ISS. And here's the water dump. Actually, Discovery held it for 10 days because they actually didn't want to contaminate the COBE module on ISS. All right, so if you had if you do a continuity equation here for to get the surface density of water, you know, it's really sources minus losses, right? And the source, of course, is the water flux from Orion. While the losses, there's a whole host of losses, actually very similar to what LADEE describes, like thermal desorption, photon-stimulated desorption losses, photodissociation, where photons come in and break out the water, electron-stimulated desorption, migration, although in low gravity you probably won't have a whole lot of cross-migration across the asteroid, including sputtering, just a whole myriad of losses. But if you assume, for example, these losses go to zero, so you might have a cold, dark surface, low gravity, then in fact, this just is a trivial differential equation to solve where the surface density varies linearly with time. So if you used, if you're out a kilometer away from something like the shuttle, and look at the flux accumulating, you actually accumulate about 10 to the 18 waters per meter squared per hour for exposure, and after about 10 hours, you would develop a water layer. So this cold trap approach is the upper limit. What really happens in reality is, of course, you have a finite temperature, so there's a fast loss. And that loss is thermal desorption, where a warm surface releases water. And what happens is really these waters come in and they get trapped in a potential well, a van der Waals potential well. And how they stay trapped and the degree to which they stay trapped has to do with this activation energy here. And if you have a nice regular crystal, this mound ends up not being very large, little bump in energy. But if you have a defect, this actually jumps up. So if you use, folks who'd worked a lot on this were actually our NSLI colleagues at APL and down in Georgia Tech, where they did temperature programmed desorption studies of water off of various materials. And they actually could derive a residency time or sticking time for the water here, which goes as the exponential of the activation energy, this bump here, divided by the surface temperature. And again, typically you get larger U's, larger activation energies for crystals with irregularities or defects. So defects end up playing a big role on this, like a weathered surface. Now what I have plotted here is the residency time or sticking time, if you will, as a function of temperature here. And it's really interesting. If you have a surface that's sort of defect-free, so you have a low activation energy, and it's warm, gosh, the water only resides there for a nanosecond, even less than a nanosecond. But if you have a high activation energy, a higher trapping potential, if you will, and it's a little bit cooler, you can actually get times on here on the order of a day and above. I only plotted it to a day, it can be above. And a nice discussion of defects, can't quite see it down here, is Darby Dyer's 2010 paper, where she actually introduced this idea of defects in terms of, where she discussed this idea of defects affecting water's ability to stick to the surface. So let's consider now a case study, and some of this is a contrived geometry, but let's consider a case where you actually have both a source term and a loss term. We assume the moon, we assume a moon-like asteroid surface temperature profile with like 400K at the subsolar point and 100K, that should be subsolar point, and 100K at the terminator regions. You're about 1 kilometer away, and assume you have a shuttle-like source. Now, it may not be like a shuttle source, and we'll talk about how it may vary, how this result may vary. In that case, from hot to cold here, low latitudes to high latitudes, or what you find is that you get a wide variation in residency time, from 10 to the minus 10 seconds for low activation energies to upwards of a day and above at higher activation energies. This results in, let me see here, there we go. I'll move past that. There we go. This results in water flux that actually, keep in mind, this is 20 orders of magnitude here. Water fluxes that could be as low as 10 to the 4 waters per square meter, all the way up to 10 to the 20 per square meter, which is actually, you're getting up near a monolayer. Now you do see a temperature effect. So as you go up to higher latitudes, the temperature drops and the water will tend to stay better adsorbed, sticks longer to the surface. But you see the primary driver here is this activation energy, the nature of the defects. So the key takeaway here is temperature is important, but defects seem to be a strongly defining variable. Let me just move here. Here we go. You might ask the question, let me just go back here for a second. Given this broad range in activation energies, what activation energy would you pick? You know, I know Dana and I have had this question. Do you pick, 0.7, 0.2? In fact, it's probably a statistical situation where if you grabbed a handful of regolith, you have many adsorption sites, some with relatively low activation energies, and then progressively fewer at higher activation energies. You can think of them as like a Gaussian in distribution of activation energies for a group of, for a handful of regolith. And so with that in mind, the really approach here is a statistical approach for activation energies where you actually define a Gaussian distribution with most of the activation energies at lower values, but some going up to higher values. If you define a width of this of 0.3 EVs, then you find that for the most part at low latitudes, the water does not stick, but at the terminator and cooler regions, it actually you get a lot sticking. Not a lot. You get the tail of the distribution, a larger fraction of the tail of the distribution sticking. On the other hand, if you expanded that distribution, then you get many more water sticking because you actually have many more adsorption sites up at higher activation energies. So you actually will tend to find that water sticks more to a defect-rich and weathered surface. So one thing that we're suggesting is if you actually do have this, if you actually have the astronauts out there, one thing that they could create is an asteroid defect garden to test some of this. Where, because we seem to think that defects strong controlling element here. Like they might lightly overturn regolith, so maybe that sample might be more pristine. Okay, and then you could actually put fractures into the surface by hammering it with a hammer. So now you've got new grains with fractures in them, but that's one kind of defect. You maybe even have the astronauts fire a laser at it and to mimic impacts, but laser ablation. And then you can also lay down surfaces with known materials in the garden. And over the stay there, over the time that they dwell, use infrared spectrometry to examine the water retention. And you might consider this as the analogous of long-duration test facility. So to conclude, key takeaway number one: Orion is a source of water and will most likely be the dominant exosphere in the two-object or Orion asteroid pair. Water sticking time is defined by the Plany-Wigner equations, with sticking tending to be more, with water sticking longer in a defect-rich surface. And in fact, maybe approaching even a monolayer. Another key takeaway is that weathered surfaces and the distribution of defects tend to be a stronger variable, maybe even stronger than temperature. And I know we focus a lot in implantation studies and adsorption studies on temperature variations, but don't forget about the defects. The defects really seem to be a strong modulating effect here. The surface water, depending on the nature of the defects, can vary. Can be any wide range of value, but it's probably best describing to get an answer. You have to look at it statistically and get at that distribution of the defects. And key takeaway number three: don't do water dumps near that asteroid, please. That just dumps a whole lot of water, and I'm sure other stuff onto that asteroid. All right, thanks so much. That's it.
We have time for a few questions. All right.
Paul Ogle, NASA Johnson. So, Bill, really interesting. What is your sense of astronauts doing EVA and their contributions to the exosphere?
Well,
when you're actually at an object.
Yeah, I mean their own gas in some sense, their own outgassing. I mean they'll probably have their own environment as well that they'll carry with them. Actually, that's a good question.
So, given the proximity and their exposure during EVA, how much is that going to? Will this still dominate, or will the EVA dominate? I guess that's what.
That's a good question. Yeah, that's a really good question. It really depends on how much they're outgassing themselves. Don't know. Don't have an idea about that. That would be actually an interesting side study, actually. But you're right. So there's this contamination all over the place, really. Firing a thruster. I don't know if you saw Dana Hurley's talking about Chang 3 coming in. And leaving a layer of water on the moon and other stuff. So it's analogous. All right, good.